everybody? There's another lecture.
Yeah, I think they're just finishing up.
Okay. I was late.
They should be here soon.
Everybody else is later than me.
I'll go around. Alright, anyway. Thank you very much.
It was very basic.
Okay.
Just
Okay.
When I first started doing that, I'm sure the recaps were available in an hour. It was like 3 or 4 recaps.
Oh, what address up here?
Does this thing work? Hello? Oh, no. Right. Okay, do you think everybody's here, just about? How many should you be, do you know? 20? 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, right. Okay, we're all a bit late. Right, last week I introduced you to thermoplastic pipes, manufacturing process for making thermoplastic pipes. And just before the end of the lecture, we got on to applications of these thermoplastic pipes. These are, if you like, pipeline engineering applications. So these pipes are used very, very widely in gas distribution and water distribution, but they're also used in the oil and gas industry for the transport of various fluids. I just want to go through some of the, I think I started on this, but I want to go through some of the applications. So, flow lines, low pressure, less than 15 bar flow lines for water, gas and oil and various mixtures. Very important application, which I'm going to deal with, not mainly today but next time, is in liners for tubing. So you can take a carbon steel tube and you can take a fluid which would normally be highly corrosive to it, and you can make it viable just by installing a thermoplastic liner. And you can also use thermoplastic liners to rehabilitate existing steel piping if it's badly corroded. And that's actually a major business area now for thermoplastic pipes. Also, thermoplastic pipes are used, or thermoplastic tubes are used as liners for all sorts of different pipes. I'll mention these pipes in a later lecture. These are composite pipes, pipes made with carbon fibre or glass fibre. Also, the large diameter flexible pipes that you see at companies like Wellstream. Do you get a trip to Wellstream? You should ask. Well, did you say no?
GE Wellstream.
GE Wellstream, yeah.
We're going next week.
Okay, that's good. You'll be impressed. But the key component in those pipes, the thing that stops them from leaking, is hey guys. The key component in these pipes is the thermoplastic liner. So I'm going to talk generally about thermoplastic liners, but there's one problem. There's one technical problem with all of these thermoplastic liners, and that problem is that problem is that gas can diffuse through the wall of the liner. So if you're using the liner as a liner for a pipe which has either natural gas or indeed crude oil with a gaseous component in it, the gas under high pressure can diffuse through the thermoplastic. Thermoplastics allow gas to diffuse slowly, but it happens. So if you have one of these pipes and it's been in use for a long time, then the pressure of the gas at the interface between the thermoplastic liner and the pipe wall will be equal to the pressure of the gas inside the pipe, which is not a problem unless you depressurize the pipe. And then if you depressurize the pipe, if you have to take the pressure off for some reason, there is gas present between the liner and the wall of the pipe, and there may be uneven areas in the wall of the pipe, there may be welds, there may be little spaces between the liner and the wall of the pipe. As soon as you remove the pressure, then of course this gas in the interface and in the annulus between the thermoplastic liner and the pipe wall can expand and collapse the liner. So there's a big problem with using these things in oil and gas because of liner collapse, and this problem exists in all of these types of pipes. You have to be careful. There are various methods of getting around this problem. This is one of them. This is called safety liner. This is a thermoplastic liner which actually has grooves on the outside, and the purpose of those grooves on the outside is to allow the permeated gas to diffuse along the pipe, where it's periodically either stored or vented. So every few kilometers the pipe might be vented, or the diffused gas might be collected to stop this collapse problem. However, it's not a problem, the collapse is not a problem when you have aqueous fluids. So take the example again that I said of a steel pipe. If you had something which is very corrosive in the steel pipe, most often in the oil and gas industry, it's injection water, because injection water contains a lot of oxygen, and it also contains various dissolved salts, most of which are corrosive to steel. So you can take a pipe that's used for injection water, which might have a lifetime of about a year, and then you can make it into a pipe which has a lifetime of 20 years by lining it with a thermoplastic liner. And this is big business, putting thermoplastic liners into steel pipes. It's used for rehabilitation, but also more and more thermoplastic liners are being put into steel pipes from new. So you might find yourself in that business, you never know. And there are three processes which I mentioned last time. The most widely known is the process which is called swage lining. These thermoplastic materials are viscoelastic. You can deform them quite a lot, and then when you stop deforming them, after a period of time they spring back. They slowly spring back. So what you can do is you can take a pipe and you can neck it down, either by pulling it, that's pulling it through a roller box. That's a box of profile rollers which roll down the pipe and decrease its diameter. Or you can sometimes pull it through a die. Sometimes you have a die here which is lubricated, which will neck the pipe down. So what happens is when you pull the pipe through this roller box, it necks it down, it reduces its diameter, and it means you can draw it, you can pull it into an existing steel pipe, and it doesn't touch the walls of the steel pipe. So you can pull a long length, you can pull a kilometre or more of this into a steel pipe. And then when you let go of it, the thermoplastic liner will retract and will swell back up to its previous diameter, which means it'll tightly grip the inside wall of the pipe. It'll press against the inside wall of the pipe. So you have a very, very good repair. It's not a bond, but it's a very good repair. So that's called swage lining. If you want to know about these processes, just Google them and go on Wikipedia. You get plenty of pictures of the pipes being installed and things like that. Right, that's swage lining. Simpler one than swage lining is slip lining. Here the thermoplastic pipe is just a clearance fit on the steel pipe. It's significantly smaller diameter than the steel pipe, and you can just pull it in. Of course, when you're using these liners for rehabilitation, you have to be careful, because of course the steel pipe might have all sorts of problems with it. It might have coatings, it might have deposits of various things that have been in the pipe. There might be rust problems. Certainly the inside surface of the steel pipe stands a good chance of being very uneven. So in some circumstances, it's better to use slip lining. So there's slight slip lining, and I say this very highly simplified diagram here, but you can do it with a kilometre or more of pipe. Usually your pipe, the thermoplastic pipe, will come on a big drum, and it'll be drawn in. And then the other one you can use is a deformable liner. There you just take the pipe, you take the plastic pipe. These are a thinner walled liner. You take the thermoplastic pipe and just fold it up into this U shape. And to keep it in this shape, you put little ties around it. You know, like the thermoplastic cable ties that you see in electrical distribution. The ties, which exactly the same as those. So you have about every metre there'll be a thermoplastic cable tie which goes around that, which stops the thing from springing up. So you pull that into the pipe. You've completely got it inside the pipe, and then you pressurise it. You pressurise the liner. All these little ties break, and the liner will then expand and fill the pipe. And I've mentioned some of the materials which are used here, but by far the most common material, as far as you're concerned, is polyethylene. Or cross-linked polyethylene, sometimes used, PVC sometimes used, and the other materials which I mentioned are also used. GRE is glass reinforced epoxy. I'm going to talk about that in a later lecture. That can be used as well. So that's pipe lining. This just shows the jack which is being used for pulling one of these thermoplastic liners into a pipe. So there's a 40-ton jack assisting the pulling of an HDPE liner into a host pipeline, and you can see it's in the middle of the desert somewhere. So that's serious business. I mentioned liner collapse, this horrid looking picture. This is what happens with liner collapse. This is what happens when the gas permeates through the thermoplastic and forms an equilibrium pressure of gas at the interface between the thermoplastic and the steel pipe. Then you depressurize the steel pipe, and the gas then tries to expand and collapse the pipe, and it'll all rush to one place. If there's a weak place, the gas can move a few hundred meters to find that one weak place, and that's the sort of thing that you get, and that's generally undesirable. You don't want that to happen. So as I mentioned, there are various methods of avoiding that. The principal one is to let the gas diffuse along the pipe and collect it periodically, but the other one is to use systems which don't contain gas. So for water-based systems, it's great. They're actually installing new lines now for water injection with polyethylene inside the steel liner. Right, this is another process, something completely different. Have you come across pipe coating in the rest of in your other lectures? With steel pipe? Yes, no? No? Right, so you've only dealt with the steel pipe itself, but you know that when you have steel pipe in the form of a flow line, it usually has to be coated to protect it from, coated externally to protect it from corrosion. And there are various things you can coat it with. Probably the most common material that's used for pipe coating is a tar type pitch material. That's the cheapest. But actually, thermoplastics are now quite widely used for pipe coating. And the way you do this, here's your steel pipe. It's preheated in an oven, and you have a length. It's not a continuous length. It's about 9 meters. So you preheat the steel pipe in an oven. Quite often you apply some bonding agent to the surface of the steel pipe to make the thermoplastic stick. And then you have a thermoplastic extruder, just like the one I described to you for making pipe, except instead of making pipe, it makes a flat sheet. So the extruder extrudes a flat sheet of, say, polyethylene here, and then the pipe is passed through it and it's rotated and moved at the same time. So the pipe is helically coated with this external coating. So that's quite widely used. So a significant tonnage of these polymers is used for coating steel pipe for external corrosion protection. Various processes are used, but this is the most common one. The steel pipe is sandblasted and preheated to aid adhesion, and quite often there's a tie layer included in the you can actually, I didn't describe this with the extrude, but you can extrude more than one plastic at the same time. If you want to extrude two plastics at the same time, you have two extruders, and then you can combine the two streams. So you can extrude a thermoplastic sheet which has on one side of it a tie layer which will cause it to bond and stick to the steel. Because polyethylene doesn't generally stick to things very well, as you might have noticed. So there you go. And of course the end is left uncoated, because of course you have to make field joints. So you make, when the thing goes out in the field, you have field joints, and these are welded, and of course the polyethylene has to be kept away from where the thing is welded. And then after the weld has been done, the uncoated area can either be coated with tar or usually a polyurethane polymer, which you can process as a liquid, just a two-component polymer which you can mix up. Right, so that's pipe coating, which again you'll probably come across in your other lectures. Right, so this is the end of my first lecture, so we're half an hour into the second lecture. Just getting to the end of the first lecture. Let's just go through. We've examined applications of polythene, cross-linked polythene, nylon 11 and PVDF in pipes. With PE, only pipe grades should be used in pipes and liners. There are lots of many different grades of polyethylene, but you can only use special grades, which I'm going to talk about probably later in this lecture. Only these pipe grades. And the pipe grades are called things like PE80 and PE100. I'll tell you what the most common one is PE80. I'll tell you what that means later on. They're actually bimodal. They have a special molecular weight distribution in the polymer, and they get better resistance to crack growth than general purpose polyethylenes. Again, more about that later. Nylon 11 is used in more demanding applications, particularly with oil at higher temperature, but you need care with nylon 11 because it's attacked by water at high temperature. So if you're using nylon 11 to handle oil from an oil well, you're not supposed to have more than 5% of water in the oil. PVDF is also very good, has excellent chemical resistance up to higher temperatures, but at low temperatures the ductility is limited. So when you go and visit Wellstream, you'll see the liner being extruded around the steel carcass of the pipe, and you can ask them what polymer they use, and it'll probably PE80 or PE100, but you can ask them whether they use nylon 11 or PVDF as well, and the answer will be yes for special applications. So that's the conclusion to the first lecture, and there's some revision questions, and they're like the sort of questions that I might ask you in an exam, not the exam question, typical of what I might ask you. Right, so let me come out of this and get into the second lecture. Lecture number 1. Just a little bit more about the structure of these polymers that we use in pipes. I've done some of it already, but we'll do a little bit more. Right. I want to talk first about the structure of what we call semi-crystalline thermoplastics, and then how knowledge of the behavior of these materials are used to qualify them for use in pipes, because this is all governed by standards. You can't just take any old thermoplastic and put it in a pipe. You have to follow standards. Right. All of the polymers that we deal with, all of the thermoplastics that we deal with, are what we call semi-crystalline. That is, they consist of long chains. Here are your long chains. But these chains can line up next to each other and crystallize, just the same as any other solid can crystallize. But there's a problem, and the problem is the chains are very long. The chains have a molecular length of, say, 100,000 units or something like that. So when you see the formula for polyethylene, which is CH2 to the N might be 200,000 or more. So these chains are very, very long. So you imagine when the polymer is molten, all these chains are randomly arranged, and then the material wants to crystallize. How can it crystallize? Because the problem is, if you're just looking at one region within the material, the chains are much, much longer than that region. So the ends of the chains will be very far away from the area that we're looking at. So the only way it can crystallize, if you think about it, is for the chains to fold, to line up next to each other and then fold. So you get a lot of chain folding. But you also get some chains which are trapped and which go from one crystal into the next. The polymer physicists used to have long arguments about what the structure of these semi-crystalline thermoplastics look like. You can use X-ray analysis. If you use wide-angle X-ray analysis, that will show you that the material is crystalline, and that the chains line up with each other, and it'll give you all the dimensions of the crystalline unit cell for the thermoplastic. If you use low-angle X-rays, which you may not have come across before, low-angle X-rays will identify. You see here, you have crystalline region, amorphous region, crystalline region, amorphous region. You have this sandwich structure of different regions, and the amorphous region has a lower density than the crystalline region. So this structure will scatter low-angle X-rays. So physicists used low-angle X-rays to identify that not only was the material crystalline, but somehow there was a periodic density change, like the structure that I've shown you there. So okay, this is a sketch, but it actually turns out to be a fairly accurate representation of what the crystalline phase looks like in thermoplastic pipes. And this phase makes it very tough. One of the things that I want you to notice about this crystalline phase, actually, see that one there? That's what they call a mistake. When I was drawing that, it was late at night. But you can see that you have one of these crystals, you have one, if you just follow one of these chains, when it gets to the surface of the crystal, it can do one of three things. It can either turn around and go back, it can fold, or it can go into this amorphous region and wander around for a bit, and then go into another crystal. Or it can go almost straight through. And the ones that go almost straight through are called time molecules, and they're called time molecules because they hold the material together. They're essentially the material that holds the entire polymer together. So this resembles a two-phase material. The amorphous material has what we call a glass transition temperature, which is usually below room temperature. So what happens is that this amorphous material can either be hard and tough, or it can be rubber-like, depending on whether it's above or below the glass transition temperature. And the crystalline regions hold the material together if it's above the glass transition temperature. And semi-crystalline polymers are very tough and ductile, the best example being polythene. Right, I've said rather a lot there. If you look at Young's modulus versus temperature for these materials, it always looks like this. The values are different from polymer to polymer, but it kind of looks like this. So at low temperature, you have a particular value of Young's modulus. It's usually about 2 or 3 gigapascals compared with the Young's modulus. You know the Young's modulus of steel? If you don't, you should do, and you will do. Somebody tell me the Young's modulus of steel.
Like X65.
What?
Like X65 steel. It's around 10,000 megapascal. What's around 10 megapascal?
I'm asking about modulus, not strength. Young's modulus of steel.
2.1 into 10 power 5 megapascal.
Say that again.
2.1 into 10 power 5 megapascal.
210 gigapascals.
Megapascal.
You're right. Just remember 210 gigapascals. That's one thing that you'll always remember because you do all the calculations. Right? So steel has the Young's modulus of 210 gigapascals. The materials I'm talking about have a Young's modulus of about 2 gigapascals. So they're a lot less stiff than steel. So at low temperature, you've got a modulus like that. As you go up in temperature, it falls off a little bit, but then we get to this region which we call the glass transition temperature of the amorphous phase. And at that temperature, the amorphous phase becomes very weak, and the Young's modulus falls right down. So the Young's modulus of the entire system falls down, and then you go into another region where the material is tough and ductile. You probably noticed if you played around with plastic polythene bags. Polythene at room temperature has this sort of behaviour. It's very tough and very ductile. So that's the sort of regional behaviour that you get. And then if you go up to a higher temperature, we get up to the melting point, and the Young's modulus goes down further. The difference here is the size of this step when you pass through the glass transition temperature depends on how many crystals there are. If there are a lot of crystals there, then you have a high Young's modulus. If there are not many crystals there, you have a low Young's modulus. And again, the best example of that is polythene, because there are different types of polythene. The polythene that we deal with in pipes is what we call high density polythene. It's a density of about 0.96 or something like that. Specific gravity rather, 0.96. There's another polythene called low density polythene, which has a lower density of about 0.92. So it's only the difference between 0.92 and 0.96. But there's about a factor of 10 difference in Young's modulus between them. And you don't use low density polythene. Low density polythene is like the sort of polythene you use in packaging. It's not used in pipes. So all the pipe polyethylenes are high crystallinity, high density polyethylene. So that's what Young's modulus versus temperature for one of these materials looks like. This is what the stress strain curve looks like. In fact, this is quite important. At low temperatures, the stress strain curve of polythene, so that would be polythene at about minus 100 degrees C, or if you like, it could be nylon at room temperature. It goes up, it's not exactly brittle, there's a little bit of plasticity before the material fails, but it's quite a high strength. The strength value here is about 80 MPa, which compares with what's the strength of steel?
200.
That's James modulus. I want to know the strength of steel.
586.
It's what? Say that again.
586 megapascal.
Yeah, it's 300 megapascals. Okay, so that compares with about 80 megapascals for these plastic materials. But if you go above this glass transition, and this is like the way polyethylene behaves at room temperature, and this is quite important because we'll see this behaviour in the way that pipes fail. So here, if you do a stress strain measurement on the polyethylene, it will get up to this point here and it will neck. The material will neck down in just the same way as you see a neck in a steel specimen. I think I mentioned this last time. It will neck down, but unlike if you take a metal specimen and pull it necks down, it will fail. What happens with these plastics when it necks down is it aligns all the molecules in the region of the neck. So all these thermoplastic molecules align up on the neck. The material effectively works hardens. So this neck is actually stable. So it will yield here, and there's a load drop. It will yield, this is the neck which forms in the sample. And then this necked region will propagate all the way along the sample. I'm sure you've probably done this yourself. If you take bits of polythene and pull them, you see what happens. The neck propagates all the way along the sample until all of the sample is necked. Now that material is actually quite strong. Because for instance, if the cross-sectional area here changes by say a factor of 4, then the true stress is about 4 times higher than that. So you are actually creating very strong materials. And in some areas of polymer technology, like in tire cord and in synthetic fibres, that can be used. In pipeline technology, we don't use that. But it's just interesting we should know. So the material will neck down, the neck will propagate all the way along the sample until all the sample consists of necked material, and then the load will go up again and the thing will fail. So that's what the stress strain curve looks like. And that's important because this necking phenomenon determines how the material will behave in a pipe. Again, I mentioned it last time, but I'll show you again. The other thing is to look at this. If you look at the material under an optical microscope, have you done any microscopy of metals yet? Yeah. It's microscopy of polymers are different. Microscopy of metals, you polish and etch the material to bring out the structure of the grains, and you look at it in reflection. With thermoplastics, you cut a very thin layer. You have a very thin slicer. It's like a razor blade. You slice a very, very thin layer of material and look through it, illuminating the other side with a light source. So it's actually a transmission optical microscopy. And I ask you, what do you see when you look through a very thin sheet of thermoplastic? And the answer is nothing, because it's transparent. So what you have to do is you use Polaroid. You have 2 layers of Polaroid. So before the light goes through the thermoplastic, you pass it through 1 layer of Polaroid, which polarizes the light, lets through the light just polarized in one plane. And then after it's passed through the plastic, you have another sheet of Polaroid, which just lets through light polarized in another particular plane. And you know about Polaroid. If you get 2 sheets of Polaroid, you put them with the planes parallel to each other, you see white light. If you turn one at right angles, then you see dark light, because the second sheet of Polaroid stops the light which came through the first one. Well, to see detail, this is what you see if you look at thermoplastic through Polaroid. And the reason for this is that these crystalline regions rotate, they're optically anisotropic, they rotate the plane of polarized light. So there are things in here, the fact that you get this sort of pattern tells you that there are crystalline things in there. It tells you that there are crystallites which look like that. And it tells you another thing, this shape. You see, each of these look a little bit like grains in a metal, don't they? They've grown. These things are called spherulites. They grow, They start at a central point, they grow out, and sometimes they meet and impinge on each other. And here, these are spherulites, and very well organized spherulites in high density polythene. They impinge on one another, and they do look like grains in the metal, but there's a difference. And the difference is you can see this pattern. Each one of these grains has a center, and the grain has spherical symmetry around that center. You don't get that in a metal. In a metal crystal, it's the same all the way through. It's the same orientation and all the way through a grain of metal. So this isn't a grain, it's an assembly of crystals. And it's an assembly which does actually have this structure. And the question is, how can you rationalize, people spent a lot of time arguing about this, how can you rationalize this type of structure which is sketched here with what you see here, because they look completely different. The other thing that you can figure out from this, this incidentally is called a Maltese cross pattern. It bears a vague, I don't know if we've got any Maltese people here, it bears a vague resemblance to the cross, which is the symbol of Malta. But what that means actually is if you go around the spherulite, it goes light, dark, light, dark, light, dark. And what that means is that these crystalline regions rotate as you go around. And you can actually show that the crystalline chains go round the spherulite in the tangential direction. And this caused people a lot of trouble, because physicists a lot of trouble. They think, trying to figure what is the actual structure of the chains in one of these semi-crystalline polymers. People talked about, they thought perhaps the chains wrapped around like a ball of string or a ball of wool. Of course, that would be no good, because there'd be nothing to hold it together, and that doesn't happen. What actually happens is the structure that you see. Oh, there's another picture. That's another type of polymer. That's actually, I think that's a rubber. But this is a picture of the way, right near to the centre of one of these spherulites, you can see what happens. You can see you've got these things radiating outwards. It's like a sheaf of corn or grass or something like that. The material radiates outwards from the centre. So that's what's happening at the centre of one of these spherulites. So there's something that radiates out, and they're actually flat sheets of material which we call lamellae, which is just Latin for flat sheets of material. So these lamellae radiate outwards from some initial point of nucleation. You do the sketch. What happens is that when the material crystallizes, you'll get, say, this will be the first one to grow. This lamella will grow outwards, so it's a flat plate of crystalline polymer. It grows out sideways, and the surface of this lamella acts as a nucleating point for other lamellae to grow. So the next ones that will grow will be these two here, and then you'll get more and more nucleated by the crystals which have already grown, and then you'll get further lamellae growing in the spaces between the original ones, like that. So that's the structure that you see. That's what you see near to the centre of where these crystals grow. And when you look at it, you can, if you get an exam question on this, you have to practice beforehand, practice drawing the chains. It's an artistic achievement. This is what happens. So if you look at one of these lamellae, the crystalline chains actually go through the lamellae. Okay? So the way these crystals are trapped, you can see this does actually have this. This does actually have this structure that I was telling you about. So you see chains go from one lamella through this amorphous region into the next one. So if you look at a little bit of material out here, it looks like this. So that's the structure. There's a lot of material in a short lecture. But that is the structure that you get in these crystalline polymers that we're dealing with. There's another example. These are again are spherulites, and actually these are the spherulites actually in the wall of a polyethylene pipe. And you can see something interesting here. This is a slice through the wall of the pipe, looked at under the optical microscope, and you can see this is the outer surface of the pipe, and this is not the inner surface, but it goes inwards. So this is the region near to the outer surface. And you can see this outer region here has been chilled. Because remember the process, the polymer melt goes into a bath of water, the outside is suddenly chilled. As with steel, if you chill it when you're solidifying it, you get very, very fine grains. So you get very fine spherulites near to the outer surface, and then you get larger ones at the inside. So you get small spherulites in the skin region where the material has been rapidly cooled, larger spherulites in the core region. So morphology with large spherulites is less resistant. I still haven't mentioned this slow crack growth thing. I'm going to come to that in a minute. But slow crack growth is something which is important in pipes. Right. This shows the two, in fact I'm coming to slow crack growth. This is the two types of failure that you can get in a thermoplastic pipe. This is ductile failure. Did I bring a pipe along with this last time? Did I show you one? No, I'll bring it next time. This is what happens if for instance you do a pressure test on a thermoplastic pipe. This is what you get, or this is what you should get. Also, if you have the pipe under pressure for a long period of time, the material will creep, and the creep process is very similar to the yield process. So if you have a pipe under high pressure for a long time, eventually perhaps it will creep and it will do this. And I should explain what this process is like. I described the necking process if you do a tensile test. This isn't a tensile test, this is a biaxial pipe test. So if you take a tensile test specimen, you pull it, it yields, it necks down. What's the equivalent of that in a pipe? If you pressurize the pipe sample, then the material in the wall will start to neck down. The material in the wall of the pipe will start to neck down. So this is just like a tensile test specimen in the hoop direction. So if you see what happens to the pipe, here is your here is pipe. It's supposed to be uniform diameter. Right, here's your pipe. We do a pressure test on that. Just as in a tensile test, the material will start to neck down in one place, and it will become thinner. And the place where it necks down, of course, will be weaker, so it will start to bulge. So you'll start to get a bulge in the pipe. And the material will be thinner. So it's just like the neck down region in the tensile test. So that's what you get, except the same will happen in a metal pipe, except in a metal pipe it will burst there straight away. The metal pipe will bulge and then it will burst in one particular place. A thermoplastic pipe will bulge and it doesn't immediately burst. But what happens, in this region I said, where you stretch the material when it heals, it lines all the molecules up and makes it much stronger. It makes it stronger in the circumferential direction. So this stuff is actually stronger. In fact, they actually strengthen some pipes by stretching them, by expanding them. We'll kind of go into that. It gets stronger, but the problem is you line these molecules up, it becomes weaker in the other direction. If you line all these molecules up so that they go around here, then the material becomes much weaker in the axial direction. So the thing actually fails axially. So this is the failure mode that you get. So you get first a bulge, and then you get a crack going the other way, and it fails. And this is called a parrot's beak failure because it looks vaguely like vaguely like a parrot's beak. So we always talk about this parrot's beak failure, and that's the preferred mode of failure. So if you do a pressure test on a thermoplastic pipe and it fails like that, that's usually a good result because it shows that it's deforming in a ductile way. Now, this is the preferred failure mode, and this failure mode is the basis for all the design procedures that are used for thermoplastic pipes. So if you know what the pressure is required to cause that to happen over a particular period of time, then you can use that as the basis of your design code. Unfortunately, that's not the only failure mode. This is what happens in the story of probably just some time after the end of World War II. Most countries had a lot of infrastructure with pipes, and that infrastructure dated from about 100 years previously. In UK, it dated to the Industrial Revolution in the 1800s, and all the pipes that we had in the ground, well, most of them were either cast iron or clay, and they'd all deteriorated. They'd either fractured or they corroded. There was a huge need to replace these pipes with something that was easy to replace them with and which didn't corrode. And the material with which they were replaced was polyethylene. And I'm talking about round about late 1950s, early 1960s now. There's a huge amount of pipe replacement went on. Replacing pipes with this stuff. And it worked great, it was fine. Until after about 4 or 5 years, they started getting a lot of failures. And when the failures were examined, they didn't look like this, they looked like this. So there was a different phenomenon, a completely different phenomenon. And this is called slow crack growth. Have we come across stress corrosion cracking in metals yet? No? Well, you will do. It's crack growth, which involves an interaction between a stress concentration and some chemical components of the fluid which is in the pipe. And what happens with that crack, it's also called static fatigue, because it's like a fatigue crack, except it's not cyclic. It's a stable crack which just grows and grows and grows until it reaches critical size according to fracture mechanics, and then the pipe will fail or it will leak. And this always starts at some concentration, some stress concentration. The example that I've shown you here is a scratch on the ball of the pipe, which has acted as a stress concentration and caused this thing to grow. But I've described also, we talked about welds. We talked about hot welds in pipes. You get the butt weld. Remember I said that the butt weld in a polyethylene pipe will have a bead, and you usually leave that weld bead on. Well, that gives you a very nice stress concentration here. So slow crack growth can be initiated at weld beads in pipes. It can also be initiated in certain features of fittings in pipes. It can be initiated if you do something to scratch the bore of the pipe. Also, it can do something. It can be initiated on the outside of the pipe by scratches. If you're installing a pipe in a trench and there are sharp stones which scratch the outside of the pipe, you can get these stress concentrations, which can cause slow crack growth. So all the design procedures now, this caused a major problem in the early 1960s because they didn't know what was causing this. I'm going to tell you how we get around this problem. We have a way of getting around this problem, and we have a way in which the thermoplastic material was improved greatly in order to stop it from doing this and to make it do this. We'll come to that in just a second. Right, let's just see what I've said here. Ductile failure mode, this is the preferred failure mode. Designs and qualification procedures aim to avoid ductile failure. But this mode, obviously this is rare. So the most common cause of this is an overpressure of the pipe. This just describes the Parrot's Peak failure, which I've mentioned already. So there's your Parrot's Peak, and this is the failure mode that we use in the qualification procedures. This is most companies, again, this is Wellstream again. Most companies that make pipes have to do ongoing qualification tests. So if you visit a pipe manufacturer, or thermoplastic pipe manufacturer, usually there'll be some sort of test room, and quite often they have the pipe spools tested and at a constant temperature So they put the pipe spools in a water bath at constant temperature, and that will be the maximum temperature that they will run at. And they will pressurize them at constant pressure. You see the way I've sketched them? They're all under different pressures. So you actually have a rate, you have many more pipes than this usually. I've just shown a few. But you have several pipes under different constant pressures. So you see the way I've drawn it, these three are all under this particular pressure. And there are another two under a different pressure, and there's another one under a different pressure. You hold them under constant pressure until this happens. Until you get the mixture of creep and yield causes this parrot's beak type of failure to occur. And then you record the time to failure. And this is called static fatigue. So you visit any plastic pipe factory, you'll see that. Incidentally, these pipes, you know what I mean by a pipe spool? Just a pipe test specimen with the fittings on. So when the qualification procedure is done, the pipe must not fail in the fitting. You have to be able to design and attach a fitting which is stronger than the rest of the pipe. So all the qualification procedure involves testing of the pipe itself, not the fitting. If it fails at the fitting, then it fails the qualification. Right, what are we doing? Oh dear. I'll stop after this. This is the relationship between log of the hoop stress in the pipe and log of the time to failure. So this is called static fatigue because it's exactly like fatigue, except it's not cyclic. So you put it under a constant pressure and you wait for it to fail and you measure the time to failure, and then you record and model this relationship between, see these are experimental points, between the time to failure, which is on the horizontal axis, and the log of the hoop stress, which is on the vertical axis. And you can do this over a period of time, up to about 10,000 hours, that's a bit over a year, and then you extrapolate that into the future to the design life. And that enables you to create the rating for the pipe. But I'll start with that next week. So see you again next week. Do by all means have a look through this. See you again.
No, that was last week. We need to remember the head as well, don't we? Yeah. So when I'm maybe not there, because I'm not with that, because I'm just going like,